Welcome to the module, Understanding How Students Learn Math, Parts 2 and 3 for Secondary Instructors. We value your time and appreciate your active participation during this module. Here are a few suggested learning norms to make the most of your time. If possible, work in an environment with as few distractions as possible so you can engage and reflect. Take notes and jot down ideas and questions as needed. Lastly, use this time wisely to ensure your professional learning with university instructors is productive. Here is our agenda for today's session. The first 3 processes for learning math, strategies for implementation, connecting and layering strategies in the classroom, the final 4 processes of learning math, strategies for implementation, and summary. Here are today's objectives. By the end of this module, participants will be able to identify and give examples of each of the first 3 processes for learning math. Name and understand how to implement strategies that support the first 3 learning processes. Make connections between strategies and how to layer them to promote success and student learning outcomes. Identify and give examples of each of the final 4 processes for learning math. Name and understand how to implement strategies that support the final 4 learning processes. You learned the first 3 processes for how students learn math in Part 1, but let's review them in more detail. Our first 2 processes were visualization and directionality. Visualization is the ability to create mental images to better understand concepts. Directionality involves using order and sequence when approaching math problems. What is the connection between the 2? How can one strengthen the other? A person can picture something and then mentally manipulate the order or sequence of that image. This strengthens directionality and visualization. In math, visualization is important when reading and interpreting graphs and making predictions using the existing data to determine values not represented on the graph. Directionality starts to become especially important in the ability to rotate, reorder, and mentally navigate an object. The third process was spatial memory, or the process for remembering spatial relations between objects. What is the connection between visualization, directionality, and spatial memory? How could one strengthen the other? Spatial memory includes both visualization and directionality. This includes problem-solving tasks requiring students to visualize changes in numbers, quantities, size, shape, dimension, scale, and direction, and the relationship of these qualities to one another. Students have to think critically about shapes, perspective, and available space, ultimately intersecting visualization, directionality, and spatial memory. Figuring out the way a student learns impacts their academic confidence and allows them to start to move towards self-efficacy, but they need strategies. The more you understand the processes for learning math, and strategies for intentionally supporting these processes, the more likely your students are to experience success in math class. Let's start with an activity. I am going to give you a prompt. You will then try to match what you visualize with a picture on the next slide and put the letter in the chat. Ready? Here's your prompt. Visualize multiplying -2 and x and adding 4. Take a mental picture, and when I click to the next slide, choose the letter of the math image that most closely matches your visualization. Right, so looking at the options above, which letter would you choose to represent what you visualized? What information do we gain from an activity like this? This activity gives you insight into the way we visualize. The way we visualize depends on each person, and it is just as true with your students. Picture A, some students would visualize a table because they recognize there is a variable that they may need to solve, and a table is easy to quickly find exact values. Picture B, some students visualize a graph because they recognize the information given would look like a straight line on a graph. Picture C, you will have some students who quickly visualize this as the slope-intercept form equation. Here you can see some strategies for providing students with ways to visualize math concepts. We start with the left image. Here students can see and connect the relationship of the circle with the other conic sections, ellipse, parabola, and hyperbola, created by the intersection of a plane. The tool on the right appears first as a square and 3 triangles. This diagram becomes a tool to understand and visualize Pythagorean theorem. Now we will watch a video on visualizing math problems. As you watch, consider how you can assist students in your classroom or groups with using visualization to solve math problems.
A key component of math success is going beyond memorizing formulas and procedures, and actually visualizing concepts, quantities, and solutions. Research has shown that struggling math students can be very good at visualizing, but not necessarily the critical elements of problems. For example, it wouldn't help that much with this word problem to have a compelling mental image of a blue train. Far more effective would be seeing how time and distance relate with the trains, which could be captured in a diagram. Here's another example. Instead of a vivid mental image of a pizza, it would be helpful to visualize fractions of a circle on the way to a solution. So how can visualizing math be improved? Well, one tactic is to coach diagramming solutions to word problems. Take our last example with the pizzas. 4 diagrams could be presented to a struggling math student who has to select which one connects to the problem. B, or the set of 3 circles divided into eighths, is the correct option for this word problem. Multiple choice is a good stepping stone towards independent diagramming of solutions and math visualization.
Let's quickly reflect. How can you assist students in your classroom or groups with using visualization to solve math problems? How will this impact student learning? Pause the video at this time and jot down your thoughts. Possible responses. How can you assist students with using visualization to solve math problems? You can support students by modeling drawings, diagrams, and mental images as part of problem solving. Provide manipulatives or visual tools so they can see and build concepts before moving to abstract thinking. Encourage them to explain what they see and to use visuals regularly in their work. How will this impact student learning? Visualization helps students develop deeper conceptual understanding and reduces reliance on memorized procedures. It provides accuracy, confidence, and retention by giving learners concrete ways to make sense of problems. As students strengthen visual thinking, they become more flexible and effective problem solvers. When you think of directionality, sequencing and order tend to be top of mind. Directionality does deal with order as illustrated above, with a sequence of the positioning of the rectangle and the direction that it is moving. We also want to look at directionality as the ability to order things using visuals and then articulating that order. For example, in the younger grades, the words before, on top, beside, etc. are difficult concepts for students to grasp. These are, however, foundational skills and important in a student understanding left to right, top to bottom, and how those directions work in math versus other subjects. All right, now our second activity. Again, I am going to give you a prompt. This prompt will involve describing the relationship between shapes using directional terms. As you complete the activity, be mindful of the feelings that you experience. Here's the prompt. Describe the placement of the rhombus using directional language. What feelings did you experience as you completed this activity? What obstacles do feelings like that present with student learning? There are times when even as adults, with the vocabulary and the understanding that we get a bit confused or carry out a task in a way that doesn't exactly hit the mark on what was asked or the way we were asked was confusing. This is the same struggle that students have, so let's contextualize this a bit more before we talk strategy. Let's start with the way we see the world as children and how that changes. In reading, we learn to read in one direction, left to right, top to bottom. This makes sense when students are introduced to the number line, as pictured on the left. Numbers increase or get bigger as they move from left to right. As students progress through math, they later learn to identify directionality with a prime symbol, the apostrophe next to the A, and with subsequent prime symbols as shown with the red box around B and C that denote the direction of movement as seen in the image of the triangle rotation on the right. So the first strategy is to look at the vocabulary. Students need to understand the meaning of key terms in the tasks they are asked to complete. Using motions, giving visuals, or using varied intonation will all help students to derive meaning. For example, when asking students to multiply, ask them to think of all the ways they can say 2 times a number. The activity of seeing and saying it in a variety of ways, 2 times a number, twice a number, the product of 2 and a number, allows students to be flexible in their thinking and make meaning. Take the time to review important vocabulary and highlight key directionality words in your review so they stand out to students. You may even want to put a physical strategy behind this and any words that signal an order or sequence be underlined, highlighted, circled, or etc. The second strategy is to make real-world connections using non-math examples as often as possible for students to make meaning. For example, during the introductory phase of teaching variables, you could say, the weather is variable at this time of year. A variable is a letter representing a quantity that can change. Sometimes it is an unknown that we can discover, but it can also be something that can change. We use variables to create expressions and equations for making predictions and modeling. The more connections that can be made to express the same idea in different contexts, the more neural connections students can make between background knowledge and new information. The third strategy is to provide visuals and manipulatives and teach students to use them to solve word problems. You could present students with a word problem like, if Tim pays a $10 fee to enter the climbing gym and then $2 per hour, how could we model that? Then proceed to use graph paper to create a visual that shows the slope. In this example, the student gets to see that the visual is increasing and the answer will get bigger than the numbers we began with while developing an understanding of why slope is known as a constant rate of change. When a process can be seen as confusing, like slope or transformations, using visuals and manipulatives can be instrumental in students seeing how a process works. Here we use directionality hand in hand with visualization to help students make and retain meaning. Spatial memory allows students to see mathematical concepts in their minds and use it as a mental sketchpad to manipulate images as needed. In math, we see this most commonly in students' work with shapes, dimension, and geometry. The examples above shows the types of images that middle schoolers will encounter and be asked questions like, which of the choices is not a possible face of the figure? This requires the ability to not only see the figure, but to understand how a figure could look based on the pattern of colors on each side. In younger grades, this can look like the understanding of two-dimensional shapes. We push students' thinking into the third dimension when we bring in spheres, cones, pyramids, etc. We also see the use of spatial memory with measurement units. We can help students make meaning of spatial relationships with tangible examples, like a ruler is 12 inches, a pencil is about 8 inches. What would a whiteboard eraser be? Ultimately, students can apply their understanding of spatial relationships to a variety of situations, such as reading maps, understanding symmetry and coordinate planes, etc., which helps them connect two-dimensional math tasks to the three-dimensional world. Our first strategy is to start with the vocabulary. Much of math is directional, and reinforcing this allows us to strengthen that understanding for our students. When talking about carrying, using words like on top or above the next place value can cement understanding for some people. If teaching equations or expressions, the movement from left to right is important in understanding how to approach more complex problems where order of operations, square roots, and brackets are introduced. Next, we move to visuals and manipulatives, which we touched on a bit when discussing directionality. The more students understand the spatial relationships between objects and numbers, the more concrete their understanding of a given concept. Provide visual charts with steps sequenced or pictorial references that students can use throughout the lesson. Finally, providing more opportunity for hands-on learning gives students more opportunities to turn abstract 2D math problems into concrete 3D examples. Having students sketch, build models, or even fold paper to manipulate direction, order, size, etc., allows students to make more connections to real life and use more senses, which increases the probability that they will understand and remember what is taught. Let's reflect quickly once more. Number one, where do students tend to get lost in the visual or spatial layout of math problems? Example, aligning numbers, following steps, organizing work. Number two, what scaffolds could reduce that confusion? Number three, how might I adjust my instruction to better support students who need repeated modeling, clearer layout, or hands-on tools to strengthen their spatial awareness and working memory in math? Pause the video at this time to write down your answers. Possible answers to the questions are numbered respectively. Number one, unbelievably, it can change with the topic. Students can get lost back and forth between the visual and spatial layout with different topics. A student may combine their terms correctly, while at the same time confusing the dividend from the divisor when dividing in the same problem. Number two, one scaffold that could reduce this confusion is introducing topics with concrete, hands-on, representational pictures and diagrams, and abstract examples, and allowing the student to move between the different approaches to understand the relationship conceptually. Another scaffold is guided notes with tiered examples that help the student and teacher understand what the student still needs to master the topic. Number three, using a tiered approach when teaching is beneficial. In a tiered approach, begin with the easiest examples first, DLK Level 1. As you do more examples, increase the rigor of the problem, allow students to determine what they can and cannot do. This will help with a clear layout and finding the level of support the student needs to master the topic. A good example of this, teaching Pythagorean. DLK Level 1 would include basic math questions with answers that are perfect square combinations. Example 3, 4, 5, or 5, 12, 13 triangles, and solving for C. DLK Level 2 would include basic word problem format and math problems with a radical included in the answer, 2, 6, and the square root of 40, which would be simplified. Using a calculator may be offered, and students may actually solve for A, B, or C. The final four processes were introduced in Part 1, but let's review those in more detail as well. Selective attention is a way students process information based on what they choose to pay attention to. It can contribute to feelings of frustration or inadequacy in chaotic environments, especially for students with learning differences or sensitivity to stimuli. Sequential processing refers to the execution of tasks or operations in a specific order, one after the other. Planning and reasoning may be one of the most important of the processes in creating self-sufficient students who are invested in their learning. This is the process where students are asked to show and prove their thinking. Working memory is one of the most critical processes in learning. It is the ability to hold information in our minds while we manipulate it. Working memory capacity is highly correlated with math performance and serves math processes from the very simple counting tasks to the most complex reasoning and mental stimulations we perform when calculating statistics or manipulating derivatives in calculus. All four processes focus on the student's active engagement in the learning process through attention and memory. As we noticed with the earlier activity, much of what we pay attention to is what we remember, which in turn impacts our ability to recall it when we need it. Let's dive into each of these four processes a bit deeper and make connections to the learning happening in the classroom. Selective attention is one of the most natural ways that we as humans learn and take in information. This is the process where we tune in to something in order to learn it. Humans in general tend to focus on what draws our attention. The more interested we are, the easier it is to focus on it and take in the information being given. The less interested, the easier it is to find a distraction. Think about this in the classroom. When you pull a small group to the back of a room that isn't silent or quiet, you realize that students need to be interested enough in what is going on in your lesson to tune out the background noise. How do you think the learning process of visualization, directionality, and spatial memory connect to selective attention? If students isolate or focus on only one essential process, but not the others, then they may not be successful with their problem solving. So what can we do as instructors to increase the possibility that what students choose to pay attention to is the explanation of content and assigned with the math tasks? When I switched to this slide, what did you focus your attention on first? This is the best way to introduce strategy 1, visuals. Students are able to see a graph and focus on the information being given in one place with labels. Additionally, the graphs, charts, etc. are simple, which limits the visual distractions that students could experience when trying to extract information. A second strategy lies in the procedure itself as exemplified by the cube's anchor chart. Students can focus on one step at a time to gain understanding before they internalize the entire process and commit it to memory. When planning, think about what students must look for in each lesson and consider how you will direct their attention to it. This requires a high level of planning and requires you to understand your students and how they will respond when their attention is focused on certain things. What strategies have you used to call your students' attention to important steps or other look-fors. The next process is sequential processing. Without the foundational understanding of patterns, mathematical tasks can be very stressful for students. This concept spans from elementary with problem sets like the one pictured above, students asking to identify the pattern and then apply that knowledge to determine the missing shapes, to more complex problems like finding the nth term of a sequence or applying exponent rules to find a future solution based on the pattern established in those rules. So, how can we support students with this process? The next slide will outline some strategies, and the ideas that are repeated can be seen as best practices. The strategies for this type of processing is very similar to that for directionality and spatial memory. We start with pointing out keywords that tell us the order the task is to be carried out in terms of the operations. This practice of breaking down problems by using keywords as signifiers is an essential skill for students to have in their current and higher math courses. Students being able to make those connections from keywords in reading sequences like first, next, then, and last can be used to solidify understanding and help them see how to create a plan for solving. The build-up strategy asks for you, the instructor, to look at the task and think about how to go from a simple version of the task to the more complex. For example, starting with a pattern that grows by 2 can be connected to counting by 2 by showing the jumps it takes to get from one number to the next. Then increase the complexity of the pattern to maybe an increase of 9, and building towards finding the unknown in a pattern like 2n minus 1. Starting with related but simple foundations will allow students to have confidence and more easily make connections to what they can do even when it is more complex. Visuals and manipulatives also support sequential processing, using whiteboards or anchor charts to show students how to break a pattern down, labeling parts of a sequence, or having them create patterns with manipulatives will help them see the sequence of steps to solve a problem, reinforce skills, and increase their ability to solve similar problems. Now, let's talk about planning and reasoning. This process has been proceduralized in many ways and usually imposes a one way of doing things approach to learning. Now that you are armed with strategies, both given in this presentation as well as from each other, you can see how adapting this process to individual students is important to their academic development. Students are given a task and must simultaneously employ multiple processes: visualization, directionality, spatial memory, selective attention, and sequential processing are all in play when students plan for how to solve a problem and then determine if their answer is reasonable. This is the stage where students show the meaning that they have made, and it is important for us as instructors to pay attention to the meaning they have made and address misconceptions or highlight strengths. Planning and reasoning can be asked of students in a variety of ways. Our students need to be able to synthesize information, create a plan, and complete a task. Let's take a look at some strategies. Planning can come in many formats. A student may use any of the above methods in their plan to solve a problem or carry out a task. Knowing what forms would make sense with what types of problems streamlines a student's toolkit. The most important part here is to reiterate how important it is to plan for each problem and not rush through a problem without a plan for how to solve it. Give students a space to plan for solving problems, or even better, teach them how to create their own problem-solving spaces. Students tend to do a lot in their heads, and we need to make sure that they understand how to take the information from their heads and organize it on paper. Review what students write down. Identify any misconceptions in their plan and coach directly to it by highlighting what they have done well and have them correct the misconception. The second part of the process is reasoning, which is all about being able to explain and prove why the solution to the problem is correct. One way to see if your students can explain and prove is to ask them questions about the sensibility of their answers. You can simply ask, does your answer make sense based on the problem? How do you know? A common strategy used to have students check their work is to have them use the inverse operation to see if the math is correct. However, this is not an effective strategy when checking for reasonableness. Why? If students correctly did the math, but the operation they used to solve the problem is incorrect, or if they missed a step in a multi-step problem, using the inverse operation will tell them their answer is correct, even when it's not reasonable. Reasoning can come in written or verbal formats where you ask students to explain how they arrived at that answer and walk you through their plan and strategy. Have pre-written questions to push student articulation of thought and give them space and time to produce conjectures on mathematical concepts. What is the impact of building a habit of planning and reasoning when problem solving? There are so many benefits to a student investing in the planning and reasoning process. When a student can explain how they arrived at an answer, the information will move into long-term memory and be recalled when related content is introduced. It also allows them to build habits of great learners that will help them in the long run. Our final process is working memory. This is the hot spot of the brain because it is constantly receiving information from what we're paying attention to in the environment and our long-term memory. Most people think about the working memory as the hub for fast facts. But the truth is, that is the hub for all information where connections are made. In math class, information received from selective attention is processed, And if connections are made, the information is learned and will be retained in long-term memory for later recall and use. If connections are not made through intentional meaning making processes, the information is forgotten and is not recalled to the working memory for reference. It is important for students to understand how to manipulate what they already know as they learn new things. Imagine seeing everything as a separate and isolated skill every time you are introduced to something new. How would that impact your learning? Getting that working memory to its strongest is essential. Even as adults, I am sure we wished at some point that our memory was a bit better than it is. Building a student's working memory empowers that student to be an active participant in their own learning. Let's see how we can make this happen. The power of repetition and connection is a huge part of how humans learn. In most processes for learning math, the strategy suggests starting with the vocabulary. Language plays a huge role in the learning process for any content area, and in math specifically, we are looking at the language that calls attention to, guides, provides steps, or clarifies problem solving for students. Let's take sine, cosine, and tangent of an angle. Creating or exposing students to clever phrases or mnemonic devices to recall material is a great way to help students remember formulas. This strategy may also require front-loading related words to support background knowledge recall. In this example, opposite, hypotenuse, and adjacent are examples of related words the students should know. When chunking and questioning, we are presenting information in ways that highlight natural stops or needed breaks that support students with retaining information. This is most clear in multi-step problems where you can think about the content as a series of steps and stop at places to ask questions. You chunk the problem into palatable and logical pieces and ask questions to guide and push student thinking. Ask how and why questions as they allow students to check their plan to solve and prove their reasoning. Having pre-planned questions after each chunk will help you track misconceptions or trends that arise, as well as provide moments to review previous content or preview the next session. In this process, visuals are a reminder that can be used during practice until they become a part of long-term memory. Practice should come in different forms, but always be a bit familiar. This is a great place to loop in manipulatives, other learning processes, and make opportunities for connections. Use entry tickets or task cards that include varied but consistent practice of the skill you are highlighting. Have students share out their thinking and even create visuals of how they solve a problem. Let's watch a video on working memory. And as you watch, consider what strategies you could use in your classroom to help students with their working memory.
Working memory is where we temporarily store information we're actively manipulating. It's like the brain's sketchpad, or you might think of it as a kind of mental post-it notes. Whether we're contemplating new information, actively solving complex problems, or following directions, working memory provides both the cognitive space and the cognitive tools to process new thinking. But working memory is also a finite resource that competes with other brain systems, and it can be pulled offline when a student is distracted, anxious, or simply trying to learn too much, too fast. So, if working memory is crucial to learning, how do you optimize it in your classroom? Try starting new lessons by connecting the topic to prior knowledge. Scaffolding unfamiliar material with familiar material reduces uncertainty, freeing working memory to operate more efficiently. Avoid overwhelming students with too many ideas at once. Break lessons down into manageable pieces and make sure all students have a chance to keep up. To safeguard working memory, reduce loud or repetitive noises, make sure classroom decorations aren't too busy, and evaluate the environment for any other sensory distractions. A special note on cell phones: a 2017 study found that working memory is compromised by the mere presence of your cell phone, even when you turn it off or ignore it. Put it in a separate room, as far away as you can, to preserve your cognitive focus. The more students have to keep track of, the less cognitive capacity is available to solve complex problems. So provide scaffolds, write down or record key information, consider anchor charts, and use clear verbal and visual cues to reduce cognitive friction and guide students' attention during a lesson. Finally, don't forget, brain breaks are mental hygiene. Weave in activities like exercising, recess, meditation, and even daydreaming or sleep to allow students to clear working memory, reset their focus, and jump into a new lesson re-energized.
Obviously, we are not going to allow our students to sleep in class. But what other strategies shared in the video could you use? Let's reflect quickly once more. What strategies might you use in the classroom or with your small group to help with working memory? How can you scaffold attention, sequencing, memory, and reasoning in future lessons? Pause the video at this time to write down your answers. Some strategies you might use to help with working memory: break tasks into smaller steps and provide visual cues or checklists students can reference. Use repetition, modeling, and guided practice to reinforce key ideas. Incorporate verbal rehearsal, think alouds, and opportunities for students to restate directions or concepts in their own words. You can scaffold for attention and sequencing memory and reasoning by providing structured routines, graphic organizers, and step-by-step guides that help students follow and organize information. Use tools like timers, highlighted steps, and chunked instructions to maintain attention and support sequencing. Offer guided questioning and gradual release. I do, we do, you do. So students build memory and reasoning skills over time. We have covered a lot of great content, so let's quickly summarize our learning. When we talk about visual and spatial skills, think about how students make sense of models, graphs, or number lines. These skills help them organize work and understand place value or multi-step problems. Attention and working memory are about keeping students focused and holding the steps or numbers they need in mind. This is crucial for staying on track during complex tasks. Sequential processing is simply step-by-step thinking, following routines, understanding the order of operations, and completing multi-step problems accurately. Planning and reasoning help students choose strategies, check their work, adjust as needed, and solve problems more independently. All these processes together form the foundation for math learning. They shape how students take in information, make connections, and apply skills across different tasks. We hope you enjoyed this module on understanding how students learn math, parts 2 and 3. Please complete the check for understanding and the survey included in the Google Classroom. Thank you, and we look forward to providing continued support for your professional growth at University Instructors.